Hi. So today I'm going to talk about feature stores and how to tame them. Um, a little bit about me. So my name is Valiantsin, or you can call me Valik. Sorry. Oops. I'm an ML engineer at Floor. I started my career like 9 years ago in software engineering. Then I transitioned to data engineering, and where's data, there's going to be ML. So I started to support ML teams, and that's why I got into ML engineering work. I've been working for Flow for around 3 years. Yeah, it's going to be 3 years in on September 20th. And I'm interested in like all of the phases of ML projects. So especially the challenge of the engineering. And we actually pretty recognized brands. So 1 in 4 women in the US uses Floor, and right now our monthly active users around 70 million. So we work at a big scale here. So this was a little introduction. My agenda for today, I'm going to start with a simple example. Later on, I will look at the feature stores as a black box outside of it, right? We will define like requirements and what we expect from the system, and then we will try to actually like take it step by step and piece by piece and see how it actually works and what differs one feature store from another one. And that's it. That's going to be a wrap up. So let's start with an example. Let's build something. Let's see a typical situation. You want to build a recommendation system. How it would look like. Your data scientist would go to data warehouse, open up his or her cozy Jupyter notebook, right? Try to craft some SQLs, gather a data set from a data warehouse, maybe trying the model, try wrangling some hyperparameters, different algos, and obtain some offline metrics, right? And after that, they will hand it over to product managers to say, hey, the model is done. And the product manager would go after that to the engineers and say, hey, the model is done, let's roll it out to production. Here's Johnny, our engineer, he will do this. This is Johnny, so when he sees this. And why CSP? So like model is good, like offline metrics are great. When Johnny sees your notebook, he sees this instead of the notebook and the models and the offline metrics. He sees a complex pipeline, pulling data from different data sources using different technologies. And the nature in many cases of the data itself is different. So, and it's really hard to actually like deliver something like this to production. So our Johnny is a professional, so he did it. But the data scientist decides to switch companies, and you end up with really complex, fragile system. You constantly seeking for differences between offline and online data, right? And your product managers are demanding better metrics yesterday, right? And you hired a new data scientist, and this data scientist doesn't know heck of what's going on in those notebooks, and he decides I want to start from scratch, right? Because it's easier. Not easy for Johnny, but yeah, but for data science, yes. So imagine a situation. What if we had a tool um, that could probably solve our problems? So it will allow us to battle those inconsistencies between offline and online data, and will allow us to share the features between different projects in ML so we can reuse them. And yeah, there's a solution called Feature Store. But, oh, sorry, but there's always a but. So it's still your responsibility to design those features, right? And understand how technology works underneath it. So um, let's look at the feature store from outside as a black box first. Uh, as an engineer, what we expect from a feature store, right? Actually, like you can define a lot of different requirements, but the main two requirements are getting the data set for the data scientist or applied scientist, and low latent access to data from another service that usually engineers could just call it from their services, right? For sorry, for So for offline data, data scientist needs to provide a spine. So what is a spine? Spine is just a data frame that has entity IDs and a timestamp. We will get back to this timestamp later on. And our feature store should return just like columns with features, right? That's the ideal situation. But there's a but. If you try to look at the documentation of any feature store, you will find this thing called point-in-time join, because you pull in data from different data sources, and those data sources has different nature. They updated on different schedule, right? Some of them are populated by streaming, some of them populated by batch data sources. So point-in-time join is a must requirement for any feature store. It should like you provide a timestamp and it should pull the data that is available by that time from each data source you provide. So this is a point time journey. It will be present in any feature store. From engineering perspective, it's just simple. I want to get latest features. That's it. Ideally low latent. Just provide the user ID or item ID, whatever. So in a nutshell, the feature store would look something like this. So you got satisfied applied scientist or data scientist, you got satisfied software engineer. They have access to two different storages. One is online for low latent access, and another one is offline, usually some columnar data storage like Snowflake, Parquet files on some data lake, or I don't know, Redshift, whatever you like. And some way to spin up a ETL tool to extract this data. On the other side, we have different analytical data sources like data lake, data warehouse, and message brokers. And there's this magic in between, right? So, and this magic is the responsibility of data engineer and ML engineer. Okay, so let's take it step by step now. There are actually many feature stores, and some of them are paid services, some of them are open source. Paid services like Databricks feature store, maybe some cloud provider will give you a feature store, Tecton feature form, whatever. And there are some open source like Chronon by Airbnb, Feather by LinkedIn. They all different, they have different technologies, and they also sometimes have different names. Sometimes you will find not feature store, but feature registry or feature platform. Feature registry usually refers to that, hey, you bring your orchestration, you bring your compute environment, we will just register your features and that's it, and give you a point-in-time join. Feature platforms usually take more responsibility. They do all of that like in one go, basically providing you the platform to all of this. So let's start simple. So let's start feel this magic. First of all, we'll start with batch jobs because batch jobs are easy and it's just obvious to do. And basically every feature store out there will support this type of thing. This is a code snippet just for you to understand how typically it looks like. It's one of the feature stores. I'm not going to go into details. It's pretty much similar to other feature stores out there, but basically you define a batch data source, maybe provide a timestamp so you know like when this data arrived to the data source, right? And on the left side, you have some transformations, PySpark, Pandas, whatever you like usually, and some meta information like when the feature starts, when the feature should be backfilled, feature start time, or what's TTL for this feature view. And basically, your feature store should populate offline and online storage based on this data. So what we got in this case, batch jobs are great because they are cheap. They're easy to maintain and to actually do. They support complex aggregations. You can pull a lot of data to it, right? But at the same time, they have worse latencies. Like you may have days or hours and so on. And there are plenty of tools to support batch jobs like SQL over your data warehouse, Spark, Pandas, I don't know, Polars, whatever you like. So we identified the main problem with batch data sources, right? Let's try to battle those latencies. How we would do this? We would probably try streaming, right, in this case. Okay, let's do streaming because it's easy. There are plenty of tools out there available for us, and let's see how it goes. So again, another code snippet for you to have this visual before you. So basically, in this case, usually you would define two data sources. One is some message broker like Kafka, Kinesis, and another data source is going to be some table in your data warehouse. Why you need two data sources in this case? Because Kafka or Kinesis would usually store data for around like a week or two, depending on how your infrastructure engineer will configure it. So you need some table that will support historical aggregations for your feature store. So you can time travel to like 6 months ago or 1 year ago to train the data, to train your model. And you provide a transformation. If you have something like Spark, it's much easier because you can use the same Spark transformation for both data sources, for Kafka and Baj. You will probably be limited somewhere because Spark structures streaming has some limitations. But anyway, if you respect those limits, you can have the same transformation applied to both data sources. And what we have in the end with streaming. So with streaming, we have near real time. So we achieve something like 1 second latency or 2 seconds latency. But at the same time, it comes with cost because Spark or Apache Flink clusters are not cheap. You need to pay for like on-demand instances, for instance, or whatever. And also, they are harder to support, much harder than batch jobs. And most importantly, they usually operate on a very small time frame, like hours, days. Because if you go back, you will need to have more memory to do aggregations if you want to like count, I don't know, 3 months of data, for instance. It's just not going to be like meaningful, I would say. So, what feature stores support streaming? Actually, that's what I want to note, that even though feature stores and vendors will claim that they support streaming, they tend to do this in different ways. For instance, Hanon by Airbnb and Stripe, they support Apache Flink. And in this case, you can get actually like really good latencies, probably sacrifice with complex aggregations, but still like really good latencies. With Databricks Feature Store, for some reason, they decided that could be a good idea to pull data from your data sources to a Delta table, and then from a Delta table to online storage. So it increases latency significantly. But they will still claim that they support streaming. So when you choose a feature store for your organization, just look specifically what type of streaming technology they support and how they support it. That's very important. Yep. So now let's do a little like side note before we go further. Let's talk about data. And in particular, let's talk about analytical data. When I talk about analytical data, I do not mean the data that lies in analytical storage. I specifically talk about the data that exists only in analytical storage, something like clicks or impressions. Um, why I'm talking about this? Because they are really good. Like they immutable by design, they additive. You can do a lot of complex aggregations, and they're easy to use. They're easy to combine. So you can actually apply batch and streaming transformation to this data, and it's easy. But at the same time, that's what vendors who sell feature stores what they do. Basically, they use this data as an example. Like, hey, my feature store is great. It can process a lot of data because, see, like I can count a lot of impressions and I can do this in the most efficient way. But the problem is there's another beast in the room is, sorry, operational data. What I mean by operational data, data that exists in operational storage and that usually is copied to your analytical storage via some CDC exports or events through your message brokers. Why it's so problematic is because it's mutable usually. Like if the user can go and place an order to buy something and then can like cancel it in 3 days. For instance, you want to create a feature that, I don't know, calculates exact number of orders that user has at the moment, right? In this case, you need to pull a lot of data, see what orders were placed, check out like cancel out other orders that were actually canceled and get this like final number, right? in this case. So it's easy to do with batch jobs, but it's not easy to do with streaming jobs. And okay, how can we battle this? First, like obvious idea, let's just approximate, because I mean, for machine learning model, in some cases, just signal is signal. So maybe the user decided to cancel the order not because they don't like it, but maybe it's on technical reasons. I don't know, no money, or decided that they want to change the size or whatever. So in some cases, you can cut the edges and just approximate, and that would be fine. But you need to understand this, that you need to do this only in the case that the feature is not important, and we will get back to this statement later on. Also, I want to talk about the analytical data. Is that even though that Spark is fast, Flink is fast, it's still the analytical data sources do not get that much attention and love from backend engineers, and they usually fail a lot. They have bugs because products usually care more about like the state of the application, the state of the data in the application, and like you may find yourself, I don't know, answering the alert at 2 a.m. because some bug was released and basically the whole data is messed up, and you talk to the product manager from the team that produces this data, and usually they don't care. Like, yeah, we will fix it maybe in 2 sprints. Yeah, and you need to patch it somehow, and yeah, call it a day. And it's late by design. So as I said before, Spark or Flink, it's still like you have this latency to get this data to Kafka or Kinesis, then from Kinesis to Spark, process it in mini batches, and then get to your feature store to online storage. So yeah, analytical data is messed up in many cases. So imagine a situation. I will talk specifically about a case at Floor, but at the same time, there are many cases like this in other applications. So user in our application can go to their calendar and basically log a cycle when the period start. And sometimes they tend to forget to do this. So they may skip 1 month or 2 months. And if you rely on streaming in this case, and try to like predict right after she logged a new cycle, this data might not be available in the feature store, and your statistics might be off. And in our case, it's very crucial because those features, cycle statistics, are the most important for the model. So they drive the prediction. We have other data, but usually it's like supporting features that just gives you more accuracy in some cases, but still cycle statistics is the most important one. And in this case, this inconsistency in the data will lead to jumps in the predictions. Like, for instance, if you had like skipped few months or a few periods, and we see like cycle 28, 28, and 90. So the model will be confused and will try to do something with this, depending on the algorithm and how you clean the data. But still, it's a bad user experience. So when you work with important features coming from operational data sources, it's usually not feasible to pre-compute them. And that's the problem with the feature stores, right? So all of that was my preconditions for this one. So this is a pattern, let's call it on demand. In some cases, might be called real time, but I see that the term on demand is like privilege in this case, so it's like the most used. So what you do is you have a function, maybe some Python function, depending on your feature store, that lies between the storage and the stuff that basically extract these features. And you ask your consumers to, hey, can you provide some data in the request so I can give you other features in the final feature vector? And this is really good case for operational data that is very important for your feature, for your models. Because in this case, you can do something like this, for instance, right? So how does it look like? You have this function, it takes data, you provide the output, and maybe concatenate with other features, and you have the final feature record. Some other use cases that is similar to ours. So you may have a situation where you want to, like, I don't know, predict the estimated time of arrival of your order, or maybe you want to use features of the card state. So in this case, that would be a really good choice, the on-demand feature use or on-demand features. So what feature stores support this? Oh, sorry. Let's talk about the pros and cons in this case. So the pros, of course, the feature transformation is still in the feature store. Okay. Feature transformation is still in the feature store. The important features are consistent and fresh, but you can handle like a lot of data points. You can just provide like thousands of data points. Like it doesn't make sense in this case. Also, you can do probably don't you can handle complex aggregations, and sometimes it's really hard to blend those features with the computed ones from batch and streaming feature use. So what feature stores support this? Not many of them, unfortunately. Fees support it, but like in alpha for the last 1.5 year, Tecton supported. Databricks feature store started to support maybe a few months ago. And some other feature stores like Feature Forum supports it, but as far as I know, it's like a paid feature, so it might not be available in the free product. So okay, so I'm wrapping up. When you design new features and you try to choose a feature store, think about the amount of data you want to aggregate for your features. Think about the latency and consistency. That's very important. What features are important for your model, and what is the nature of your data? Is it coming from purely analytical data sources, like something happened in the moment, or it's a export from operational storage? In the end, the feature store is great. It's a great tool, but it's just a tool that gives you possibility to design features, but you need to understand the technology underneath. So, yep, that's it.